There's one more important topic to cover in this section, and it's called the Cauchy-Schwarz inequality. I'll tell you what it's called, but before we go on and introduce the Cauchy-Schwarz inequality, I want to pause for just a few moments and remind you of what we said in the very beginning, and that was that the dot product on Rn captured or encoded the geometry of Rn in the sense that it told us what the length of a vector was and what the angle between the two vectors was. And so I hope you haven't forgotten that one of our goals in abstracting the dot product to what we now call an inner product on an arbitrary vector space is to hopefully reproduce some of that geometry on an arbitrary vector space. So, can we do this? In what sense does an arbitrary vector space even have a geometry? That is the important question. For example, V is, say, the vector space of polynomials of degree less than or equal to 2. What does it even mean to measure the magnitude or the length or norm of a vector in P2? What does that mean? Or if we have two polynomials in P2, say, to be concrete, u equals t squared minus 3 and v equals t plus 5, does it even make any sense to ask what the angle between these two things are? After all, these aren't vectors pointing as arrows in Rn, they're polynomials. Well, in this case, we can make sense of these notions, and we can do it by remembering that each of these things, or all of these things I should say, can be written as coordinate vectors. So, for example, to answer the first question, what would the length of t squared plus 5t minus 1 be? Well, remember we can write t squared minus 5t or plus 5t minus 1 as a coordinate vector 1, 5, negative 1. And now that we've written it as a coordinate vector, we can ask what the magnitude of this thing is. And it's just square root of 1 squared plus 5 squared plus negative 1 squared. And similarly, we could take each of these vectors, replace them with their coordinate vectors, which would in this case be what? 1, 0, negative 3, and 0, 1, 5. And then we could apply the formula which tells us what the angle between these two vectors in R3 is. And so we could derive some expression for the angle between these two polynomials. So we could essentially build the geometry on P2 by borrowing the geometry from R3, because after all, constructing the coordinate vectors is another way of writing the isomorphism between P2 and R3. But what about vector spaces which aren't necessarily finite dimensional? For example, the vector space we saw previously, let V be the vector space of all continuous real-valued functions defined on the interval from 0 to 1. What would it mean to ask what the length of a function is? Or what would it mean to ask what the angle between two functions is? And it's these questions which we will answer using the notion of the inner product on V. And that's as much as I'll say. Now I'll stop this video here and we'll go on and discuss the Cauchy-Schwarz inequality, and we'll say exactly how we will impose a geometry on these spaces by using the inner product.